Hi there everyone. Welcome to the video lecture series of inverse Laplace transforms. My name is Mayur Gohil. Today I will be guiding you on partial fractions because they also help us to solve inverse Laplace transform problems. So let us see a quick review of partial fractions and then we can move on to the solving of the problems. Given say two polynomials px and qx they both are real polynomials such that degree of px is less than the degree of qx, then partial fractions deal with expressing this fraction px over qx. Okay, so you can write this px over qx in this manners depending upon qx cases. So let us see. The first case is if qx can be factorized into n factors where each root, say alpha 1, alpha 2 and alpha n, are distinct roots. Okay, so these alpha I roots are distinct. So px over qx is equals to px. So px over qx can be expressed as a1 over x plus alpha 1 plus a2 over x plus alpha 2 and so on up to an over x plus alpha n. Since each root is distinct and each of the power is 1, so you can write it in this manner. Okay, so now let us see if we have multiple roots. Say a root is repeated m times, so that is the second case. If qx can be written as x plus alpha to the power m into x plus beta, where alpha and beta are different roots, and alpha here if you see it is repeated m number of times. So now in that case p over q can be written as a1 over x plus alpha and a2 over x plus alpha square and so on up to am over x plus alpha to the power m, and the root beta, since its power is 1, it is again written as b over x plus beta. Okay, now observe that since the root is repeated m number of times, you have m coefficients to be determined, and the denominators, you see their power goes on increasing, x plus alpha raised to 1, then square, then so on up to power m. Okay, so that is one case. Now the last case is very important. If qx can be expressed as x plus alpha times a quadratic, say ax square plus bx plus c. Now you observe here that this quadratic is irreducible over r. Now the meaning of irreducible over r, it is that b square minus 4ac is negative. Okay, the quadratic, the discriminant, if you consider the b square minus 4ac, it is negative. That means the root of this quadratic are complex. That is what is the meaning of it is irreducible over r. That is, we cannot factorize it further. If we factorize it, we get complex roots. So that is the meaning of quadratic being irreducible over r. So p over q can be written in this manner. Since now alpha is a single root which is a real root and it is having power 1, x plus alpha to the power 1 over here, so it can be written like in the case 1, a over x plus alpha. Now regarding the polynomial over here, which is irreducible, its degree is 2. So over it, the numerator, it was written in bx plus c. Observe here, since its degree is 2, it is written as a linear polynomial, say bx plus c. Had it been the degree 3, it would be written as bx square plus cx plus d. Again, suppose its degree was 4, then you would write a polynomial with degree 3. So whatever is the degree of the irreducible polynomial over here in the denominator, say degree k, then you would write a polynomial in the numerator of degree k minus 1. Okay, and so accordingly we determine the coefficients. Okay, now let us move on to solving one problem using this partial fractions. Let us consider this problem. Here L inverse is, we have to find L inverse of s plus 29 over s plus 4 times s square plus 9. So this is the question. We have to use partial fraction method. Now since here we are considering partial fraction method, you have to use either of the three formats that we have just seen. So if we observe, this can be written as, the function can be written as a over s plus 4 plus bs plus c over s square plus 9. Now if you observe, this format is the format of third type of partial fraction that we just saw, because s square plus 9, if we calculate b square minus 4ac, it is negative, and hence s square plus 9 is irreducible over r, so we can write in this manner. Now what is our goal over here is that to find a, b and c. So how can we find this? We have to express this in this manner, that is s plus 29 a times s square plus 9 and so and so. So how does this format is achieved? You multiply the denominator of LHS to RHS. That is it. You just have to cross multiply this denominator over here to RHS and simplify it. So what will happen is that s plus 4 gets cancelled, so remaining term with a is s square plus 9. Similarly, s square plus 9 gets cancelled and remaining term with bs plus c is s plus 4. Now in order to find these coefficients a, b and c, you can do one thing here. You can randomly substitute values for randomly substitute values for s. So you can choose values. Say I am going to choose here, I am going to put s equals to minus 4. I am putting here. So what happens is that when I put s equals to minus 4, this entire term vanishes. I obtain value for a immediately, and that value is a equal to 1, because you simplify that equation that you obtained. When you substitute s equals to minus 4, you get this value a equals to 1. Now similarly, I am now putting s equals to 0. So when I put s equals to 0, what do I see is that this coefficient b vanishes. Okay, and I get a equation 29 is equals to 9a plus 4c, and I have already obtained the value of a over here, and then I substitute it in this equation and I obtain c is equals to 5. Similarly, when I put s equals to 1, I obtain this equation, and then I substitute value of a and c. I obtain the value of b, which is minus 1. Okay, having done that, now let us move on to substituting this a, b and c values in this expression. Substitute it over there. What do you see is that you obtained 1 upon s plus 4 plus minus of s plus 5 and s square plus 9 over s square plus 9. Yeah, so having done that, now you take inverse Laplaces, or you can simplify it in this manner. Okay, now yeah, here there is one important point. Many a times the common mistake that is seen here is, I'm going to show you, do not try to do such wrong mistakes. Many times children or students write this way. This minus is shifted and the plus is kept here. So you observe that the meaning of this statement that you have seen here, which is the correct statement, and this bold one is the wrong statement. This meaning is this. The meaning of this statement is this, which is entirely different than this. So you land up onto wrong answer if you solve in this manner. So this is absolutely wrong way to do. So let us now go to the correct way. So you write this s up your given fraction in this manner. Now you take inverse Laplace on each of the terms, operate inverse Laplace on both the sides. Inverse Laplace operator is a linear operator. Simplify for the inverse Laplaces of each of the term. You obtain e raised to minus 4t as the Laplace of inverse Laplace of 1 over s plus 4. Similarly, for the s over s square plus 9, that is minus of cosine 3t, and over inverse Laplace of 5 over s square plus 9, you adjust with multiplication of 9 divided by 9 and you obtain sine 3t. Okay, so this is the inverse Laplace by partial fraction. Similarly, you can try one example on your own, that is this. You can try completing the square of each of the terms and then obtain using first shifting theorem. Okay, so I leave this example to you to practice, and if you have any queries regarding it, you can revert it to me. I will be happy to help you. So thank you. That's it for today.